is the following statement true, that for all integers a and b, if a divides b, then a divides b² plus b. So what should we start with is thinking of some examples before we start assuming it's true or false. So my favorite examples when we need to think of something dividing something is going to be 2 and 4, 3 and 9, and 5 and 10. Those are some of my favorite examples to do because they're the easiest for someone to do in their head or just to simply see and understand. So let's give 2 and 4 a shot. So if 2 divides 4, which it does, we're basically asking, well, 4 can be written as a multiple of 2. If 3 divides 9, we're saying 9 can be written as a multiple of 3. And if we're saying 5 divides 10, we're saying 10 can be written as a multiple of 5. Where x, k, and m, and right here, x, k, m are all integers. That's what this must be true. This must be true in order for this to be true. So we already know that this is true because x here is 2, k here is 3, and m here is 2. So those are all integers, so of course all 3 statements here are true. So anyways, let's get to what we're trying to prove. Let's see if a divides b² plus b for 4. So let's say does 2 divide 4² plus 4? I think so. This is simply going to be the same as saying, does 2 divide 4 times 4, not 2, 4 plus 4, which we can factor a 2 out here. We can say this is the same as asking, does 2 divide 2 times 2 times 4 plus 2. I think that's correct. Let's quickly verify that. This up here is going to be equal to 16 plus 4, which is 20. This is going to be 8 plus 2 is 10 times 2. Yeah, so yes, it's true that for 2 divides 4, 2 does also divide 4² plus 4 because 2 divides 20. And the reason 2 divides 20 is because 20 can be written as, of course, where's a nice marker? There we go. 20 can be written as a multiple of 2. All right, let's try 3 divides 9. So we have 3 divides 9² plus 9. That's the same as saying 3 divides 3 times, 9 times 9 plus 9, which is the same as saying we can factor a 3 out, which would be nicer because we're looking for a 3. We could do 9 as well, but remember, we're trying to look for what's on the left to be what's on the right. So to be a multiple of what's on the right. So we can take 3 out here, which is going to leave 9 divided by 3 is 3, times 9 plus 9 divided by 3 is 3. Okay, and just to double check, let's do this in our head. 9 squared is 81. 81 plus 9 is 90. Is 90 the same as saying 18 plus 3, which is 21. 27. 27 plus 3 is 30. 30 times 3 is in fact 90. So there we go. We have shown that 3 divides 9 and 3 divides 9² plus 9 because this is the same as saying 3 divides 90, and 90 can be written as a multiple of 3. What's on the right is a multiple of what's on the left. Fantastic. Very last example. Let's try 5 divides 10² plus 10, which is the same as asking 5 divides 10 times 10 plus 10, which is the same as saying factoring out what we want on the left. On the right, we can factor a 5 out, which is going to be the same as saying 2 times 10 plus 2. Yes. And then if we just want to compute this in our head, is 100 plus 10, so 110. Now this is true because 110 can be written as a multiple of 5. This is saying 2 times 10 is 20, and then 20 plus 2 is 22. 22 times 5 is in fact 110, so what we have here above is what we have down here written as a multiple of 5, which is what's on the left. So in all 3 cases, we have shown that it is true that for a dividing b, for these cases, that it does seem to be that a does also divide b² plus b. So we're going to assume the statement's true. So let's go ahead and try and prove it. Now, right before we start proving this, let's just one more time remind ourselves, what does it mean for something to divide something? Well, the definition is going to be that, let's say you have x divide, or it has to, we're doing exclusively integers here, so we're going to say x and y are going to be integers such that x divides y, which means y can be written as x times m for some m that's an integer. Again, what's on the right is a multiple of what's on the left, or we should be able to write what's on the right as what's on the left times some integer. That's what this really means is this true? Can we write this to be y, and then y can be x times some integer? What's in the brackets here has to be an integer. So that's going to be our goal, is to try and use this definition to prove the statement above. How do we prove this? Well, this is a for all statement. And how do we prove all of our for all statements? Well, we begin with the word let. We say, let a and b be integers such that a divides b. Something important that I've been forgetting to do in my previous proofs, and I'm going to make a video saying, hey, I forgot to do these in the playlist, is that there's a very important statement I've been missing, and that is that a cannot be 0. Why did I forget to make the statements? Because it's something you forget. When you're saying by definition that if x is divisible by y, then y can be written as x times some integer m, if x is 0, m cannot be an integer, because if you rearrange for m, it's going to be y over x is equal to m. This has to be an integer, but if x is 0, this would be actually undefined. So we always have to state in our divisibility proofs that what's on the left cannot be 0. It must be a non-zero integer. So I'm going to make a video after this admitting to my mistake there. But now we remember this, now we can obviously make this claim. Anyways, next up in our proof, we want to probably explain mathematically what it means for a to divide b. So we say, then b is equal to a times k for some integer k. Next, so we've now assumed and defined everything we've needed to. Next, we can jump to here. We can see if this can be written as a multiple of a. So we say next, b² plus b is going to equal to ak² plus ak, which is going to be the same as saying a² k² plus ak. And then here we can obviously factor out an a, so we can say this is the same as saying a times a k² plus k. And as we could see, this is a multiple of a, because it's a multiplied by this, which is going to be an integer. Why is this an integer? K is an integer, and a is an integer. An integer squared is still an integer, and then that multiplied by an integer is still going to be an integer, and then that plus an integer is still going to be an integer. So recognize what's in the brackets here is an integer. So we say where a k² plus k is in fact an integer, so a divides b² plus b, because b² plus b is or actually we can say b² plus b is equal to a times a k² plus k, which is a multiple of a, and a always divides a multiple of itself. I was being super explicit in this conclusion, but there we go. We've now proven that the above statement is in fact true.